Okay. So anyhow, so you have already shown the time and I have circulated a play model exam. I have circulated this practice exam. So please take a look at it when you are done with the class. Afternoon, you are able to solve them. Get one? They are so whenever I have chapter ethers and alcohols. As you know, we are dealing them together because the reactions of alcohol are done. Right? So come back to ethers. We'll go back once and talk about the reactions of alcohols because the other thing is some people are worried that chapter 18 is come back in the exam. So you don't have to worry about chapter 18. Score well. Just one reaction. We already covered chapter 17. So you have to about chapter 18 exam. Chapter 13, chapter 17. So we were talking about the synthesis of our so we have a few more reactions to cover in alcohols. We'll talk about that. So this is the alcohol functional group. C single bond O, and if you have a H, you call that as alcohol. If you have an alkyl group, you call it as ether, right? So that's the only difference. For most of the reactions and structural properties, physical properties are same for both of them. So the reactions of alcohols can be classified in two categories. One where this hydrogen is replaced, so the OH bond is participating in the reaction, or CO bond is participating in the reaction, where the whole hydroxy group is replaced. So there are only two types of reactions for alcohols, right? And it can donate the proton, so it can act as an acid, and it can also donate a pair of electrons, so it can act as an acid, can act as a base. So one of the ways we looked at Neither's chapter is dehydration of alcohol. If you take two molecules of primary alcohol, difference of this, and you added concentrated sulfuric acid and removed a molecule of water, that's also called the dehydration reaction. And as a result, we made ether. However, this reaction is not selective for primary alcohol. If you have tertiary alcohol or secondary alcohol, have a result in elimination formation. Okay? In here, the sulfate is not a good nucleophile. That's another thing. The first step for all these reactions is protonation. As I said, protonation and common organic synthesis. So the first step is the formation of hydroxy group, the arrow to that hydrogen, and then the chloride is the leaving group. When this chloride is the leaving group, when this becomes protonated, this protonated leaves the alcohol. So you are talking about breakage of carbon oxide bond. The carbon oxide bond can break itself. As a result, we generate a carbocation. This carbocation can undergo various reactions. One of them could reacting with another molecule of alcohol itself. For example, let's say you have primary alcohol. This can undergo nucleophilic substitution with hydroxy. Or if you have acid, the chloride or bromide, chloride can attack also. So there are various reactions that can happen with carbocation. And instead of these two nucleophilic substitutions, it can just undergo elimination. When it undergoes elimination, you make alkene. Okay, that's the problem of carbocation mechanism. So you have carbocation mechanisms involved, especially if you have carbocation, that can result in elimination and double bond can form as a result to make alkenes. So normally you end up getting more than one product. But nevertheless, one reaction of alcohol is a dehydration to form ether. Other type of reactions to alcohol with acid, especially when you have nucleophilic species leading or provide iodine. They're called halides, right? Hydrogen halides. Uh, these acids, hydrogen halides, they can act as an acid as well as an nucleophile. So in that case, it is very alcohol converted to alkyl halide. That's one way of conversion to alkyl halide. There's another way. If we don't want to okay, but if we are like that, then only. So if we are converted to alkyl halide, protonation as a first step. Here, instead of proton, the phosphorus is acting as an electrophile, and hydroxy group is acting as a nucleophile. So the lone pair of oxygen is given to the phosphorus, and one of the bromide gets kicked out. Let's try the structure of PBr3, so then you understand. This is acting as electrophile, so the electrons are given to this. As a result, to make four bonds. So it is one of the bromides of. So you make PBr2 complex. There's one bromide is left. And I think one more alcohol will come and attack this. So three molecules of alcohol have carbon, oxygen, phosphorus, oxygen bond. And here the bromide will come back, whatever the bromide is hanging around, and it comes back and acts as a nucleophile. And as a result, it comes back open. You get phosphorus, oxygen bond. So there are two types of reactions. You got to remember that use the hydrogen of or you can just replace the whole hydroxy depending upon the reaction. That's then C, where the carbon in order to make the carbon oxygen bond, you got to protonate it or you got to convert it into a good leaving group. Hydroxy group itself is not a good leaving group. And the other reagent to convert to chloride, there is a PCl3. PCl3 that's also commercially available. Or you can use this thionyl chloride. This is called a sulfonate chloride. Double bond O. Compound. The liquid, whereas this is also liquid. These are little handle than strong acid. So here again the same reaction happens. The lone pair of the oxygen is donated to sulfur. Sorry about it. Come back. And come back. So PBR3 reaction, you just have sulfonyl chloride as a reagent. Sulfonyl chloride is electrophilic. So that's SOCl2. And this oxygen lone pair is attacking sulfur as a result of chloride takes off. As you can see here, that chloride would be still hanging around and that comes back. Now, once you donate this electrons to sulfur, the bond formation between oxygen and sulfur, chloride takes off, right, the whole species. And that chloride comes back and attacks the carbon, and then this whole thing is being moved. Okay? The advantage of this reagent is sulfur, bring that sulfur dioxide, the gas, we don't have to worry about it. We convert alcohols into chlorides. Okay, so there are three ways to convert alcohols into chlorides. One is using hydrochloric acid, or PCO3, or SOCl2. So, depending upon what you have on the lab, you can try one of these reactions. But the point that I'm trying to make here is alcohols can be converted into alcohol by treating with reagents, either haloidic acid, hydrohalic acids, or thionyl chloride, or phosphorus reagent, right? So you have to remember the mechanisms, and you have to remember the stereochemistry. What's happening to the stereochemistry? The first step, let's say we have between beta bond and alpha bond. This is coming towards you, this is going away from you, and as a result, let's say we have some other group other than methyl here. Let's say we had an ethyl group. So that's a carbon center. So the oxygen is donating the electrons, so we are not touching anything carbon and oxygen. Still this bond is intact, so that bond is in place. So in the first step, the stereochemistry is nothing happens to this stereochemistry. If you have R, you would have R. If you have S, you would have S. But in the second step, when the chloride comes back and attacks, it's coming 180 degrees away from the leaving group. Because this is bunch of electrons and this is bunch of electrons. You cannot force two clouds of electrons into one another. So it takes the attack away from the leaving group, but as a result, what happens to this single center once it leaves, this gets inverted. It's like an umbrella. You are going in the wind is coming and attacks your umbrella gets inverted, right? So the inversion of stereochemistry in this reaction. So not only writing the chloride would help you have to be able to write stereochemistry as well. So if I have the stereochemistry, as I said, I have an ethyl group there and that ethyl group is there. So when you apply the stereochemistry of this one, it's off because this is a mirror image of that, right? The code hydroxy group is forming both the right hand side or the left hand side. In other words, I'm talking about just a stereochemistry. The heteroatom is pointing in one direction, the heteroatom is in the opposite direction. So we have to pay attention to the stereochemistry of the first step, stereochemistry is intact. The second step is get inverted. So that's the final chloride of PBr3. But you get one stereochemistry because this is everything happening in an SN2 fashion. SN2 reaction, right? Everything happening in SN1 reaction. SN1 reaction, you have a leading part. The nucleophile is not in picture. So when the carbocation is formed, the nucleophile chloride can come from this side or from that side. As a result, you have SN2. So you have 50% of or 50% of S. As a result, you lost the stereochemical integrity. You get decimated by acid state. But when you have these reagents, you do a SN2 reaction. As a result, you have stereochemistry, but that stereochemistry is inverted from one side. Right? Now, I can further on that. Now, let's take some examples and do here. So, for example, you have a hydroxy group that is going in beta direction. When you want to write the product for that reaction, you know that it is converting into bromide, but what is the configuration of the bromide? That's something you have to remember. So you have to know all the mechanisms. I'm not expecting you to write each step and tell me how it is formed. What I'm expecting you is the product correct configuration, correct physical transformation. I know that alcohols are converted into bromide. Upon treatment with phosphorus tribromide. If somebody writes this structure, they only get partial credit. That's not the wrong structure, that's also bromide, that's the same bromide, just that they have depicted the stereochemistry correctly. So we have to pay attention to the stereochemistry and incorporate that into the product. Here there is no chiral center, so you can just write the bromide as you want. When you have chiral centers, you have to pay attention. For example, this has two chiral centers. We are not touching anything on this chiral center. Whatever the chiral center stays safely because there is no reaction happening there. The whole reaction is happening on this hydroxy group and PBr3. So the first step is reduction of the stereochemistry in the first attack. The second attack on the global attack comes from the angle and the product. You get bromide of that configuration. So this is a thick bond. You have a dash bond here, right? Because the bromide is now coming from the front face and this is leaving from the back face. So the tetrahedral carbon is not flat. It has tetrahedral nature. So we have to remember that all these bonds have. So in cases of where you have the mechanism, what is the reaction here? Formation. So the first step is the protonation of this hydroxy group using hydrobromic acid. As a result, you draw the first intermediate, that is oxygen attached to two hydrogens, and as a result, this can leave itself and it can form carbocation. And as a result, where with my drawing here, there's something wrong to do with this pen. Something is attached to the pen. Okay, so anyhow, the carbocation has formed, and that carbon is directly attached to that carbon. This is the carbocation, and now the bromide, whatever comes from here, will come back and attack either from the bottom face or from the top face. That's the problem of carbocation. We can note down. So that's when the use of these reagents comes to the picture. They will keep giving the physical outcome that you want. I want to convert this into a chloride, but I want to convert it in a specific manner. As a result, I can make the chloride that I want, especially in the drug industry. You need to have one figure. Okay? Oh, somebody had a question. Oh. I knew something would be. So some cases we don't give you the PI3. This is essentially making PI3. So phosphorus and iodine is like phosphorus plus bromine is PBr3. You don't have PBr3 body sitting in your hood, just use phosphorus and bromine. But in the same case, what we give you is a chloride plus magnesium and then plus aldehyde, right? So when you have to think that, okay, this is our reaction, so it's not quite within our reagent, after have not reagent, that's added to aldehyde. You have to take one step backward and then take the reagent, right? So, any questions so far? And there is another reagent, it's called copper chloride. Copper chloride is similar to sulfonyl chloride that we saw in the time. Just that one of the chloride is now replaced by benzene. There's one more option of sulfur. So the first thing is similar, that is the nucleophile ion of this oxygen onto the sulfur, and the chloride takes off, and then we make this positively charged to the oxygen. Another bond, another it has three bonds, so it has positively charged, and now the chloride itself can come and take this proton, and as a result, this is the perfect something called oxygen. So use sulfonyl chloride, if that has two chlorides, you can make chloride. But if I start one of the chlorides with this group, that can give me calcium. Okay, this intermediate is stable, it doesn't leave that easily. So the sulfur still sticks to the oxygen. This is a good leaving group, but it's stable enough to be isolated, as opposed to the intermediates that we saw in the previous slide. Okay, so these are called oxidates. And notice the stereochemical information. Let's say you have a stereochemical pure alcohol, that is copper chloride. What happened here? We're only using the electrons of the oxygen. We are not breaking carbon-oxygen bond. So as a result, the carbon chloride just gets attached to the oxygen. The stereochemistry is similar to what we have here. It doesn't get inverted because you are attacking using the oxygen, so nothing happens to the carbon center. When does it get inverted? When the nucleophile attacks the carbon center on the carbon, it leaves. So that's when the inversion takes place. When you don't touch this carbon, when you don't attack this carbon, only if you are using the electron of oxygen, nothing happens to the carbon center. So in the copper chloride formation, the first step, only if you invert it, that is something on this carbon. So if I bring another nucleophile, than doing power. And the problem is attached to the platform. So the causal chlorides are called pseudo-halides. They're not quite halides, but they can be called as pseudo-halides because they are doing the same job like a halide. What is the job of halide? Do something. That's what halides. The intermediate is not stable in TBR3. The first case, in the first step, you have oxygen attacking phosphorus and one of the bromides there, and as a result, so this alcohol is attacking phosphorus, but this phosphorus is not stable. So the bromide is coming and replacing this. And as a result, the bromide is now forming a thick bond, and the self is coming from the front face. As a result, the pseudo center is inverted. And if I do the second nucleophile substitution, I get the oxide substituted product. This is ether. So this is one of the way of making ether, right? So this is for Williamson ether synthesis. You have oxides that are attacking alkyl, but this is a SN2 reaction. As a result, I get ether in this configuration. It's a configuration. But I will make S configuration, which is low rank in if I am R here, get one inversion, and second inversion, R here. If I have to make S configuration, so this is double inversion, right? One inversion is this step, and then the second stereochemical inversion. So two inversion is equal to retention. Right? So the purpose of all these reactions is one of the things is both analyze and energy. And then go to copper chloride, PPW. You just want to just go to chloride alcohol, right? Or dehydration type of reaction. Anyhow, you got to practice these because some of these reactions will be there. So there are various slides for your practice you can think of. This is a separate problem. How do I go from this alcohol? One way is to just make an anion of this, add ethyl bromide. So if you subtract part of materials from the product, you know what it is you're mixing in ethyl group. How to bring in ethyl group somehow. After ethyl chloride, ethyl bromide, I will use nucleophile and alcohol bromide. But I look at this as zero. So you got to learn to focus on students. It's not enough to focus on the product alone. Product with the chemical information is important. So you want to try one of these reactions? Let's try quickly. This is an alcohol. We are using calcium chloride. So the first step is retention of stereochemistry. The phosphonate being formed. You can put this TOS, the phosphonate, or TS is enough. You want to just put TS, that's enough. And that stereochemistry is intact. Now I'm bringing some cythylamine. What does cythylamine do? Cythylamine is not a nucleophile, it's a base. It's the proton, right? This is the one which picks the proton. There is a proton here, 3 protons here, and there are 2 protons here. The adjacent proton. That hydrogen is picked, and this hydrogen protons are moved there. and this phosphate takes off. As a result, I can make an alkene. Because if what is used, is it a nucleophile or a base? If it was a nucleophile, I will do a substitution directly across it, and then I will go this way. If it's not a nucleophile, it's a base, then I have to do it. Right? So all these SN2, SN1 reactions are accompanied by elimination, are accompanied by SN1 reactions and SN2 reactions. So depending upon the nature of the reagent, either you get complete elimination or complete substitution. Okay? So elimination is also one of the reactions that we'll be talking about in this chapter. Yeah. Yeah. Yes. Yeah. You can that out. Also, yeah. If you don't add a heat, it will just stop. Because I see that there's a second step. The second step, the first step, for example, in this case, there's no stereochemistry to worry about because it's a reactive product. So there's no power center, so I make this possible. Why would I be using the nucleophile? So I have to bring in more CO2 and now toss it out. But again, here we have to pay attention to what kind of population we have. Is it a primary population, is it a secondary population, or is it a tertiary population? Depending upon the substitution on the center, like does it have two alkyl groups or three alkyl groups or one alkyl group, you can choose to undergo step one, step two, nucleophilic species, I can also act as a base. I would rather go to SN1 reduction and make the topocatenone, the carboxylate is leaving, and then the whole phase would come back. That plus, right? OCH3 minus, so you have a new OCH3, you don't have to worry about coding. I put you OCH3, just check the formula around. What you have to be able to identify is the electrophile and nucleophile. This is my nucleophile, so that doesn't have any override. Could be any metal for that matter, and this is all I'm interested in. This is my electrophile, and look at the electrophile, and look at the electrophile receptor. What kind of primary, it is really carbocation. Carbocation, when you have carbocation form, you have substitution, elimination form forming. So you can choose to write one of them or both of them. You would get credit for both of them. In my case, I do the partial credit. So if somebody writes an alkene, because this OCH3 minus can directly the carbon and act as a nucleophile, or you can pick up a proton from this carbon and just put that electron. So that means your 10251 knowledge is important. That's when your thought has learn on this program. Talk about what you're doing. You're taking alcohol, but you're converting them into atoms and superatoms. We're doing the same reaction that we did in chapter 11 of Chem 251. Okay, we got to practice more examples, but let's cover some more reactions and then we'll come back in afternoon maybe. So this is killing me today. Just has to go to next slide. Okay. to have that. So there's another type of reaction that we need to cover in alcohol, that is the oxidation of alcohol. We already saw reductions of alcohol, remember when we had aldehyde, we use sodium monohydrate to reduce to alcohol. We use this as a hydrogen roller. This probably has one hydrogen attached, so you can have sodium monohydrate, and then compound with hydrogen and goes to oxygen and forms an oxide intermediate, that's called tetrahydral intermediate. And second separation of water, H2O plus H2O is enough to pick up the proton from it and it becomes alcohol, right? And we also talked about esters, another compound element such as ketones, ester, and they use LH, linear polysaccharide, and then we went to alcohol. This is here was the question of hydrogen, and then was for because you have the starting material and the products, then you choose your reagent. Right? I could use LNH here, but I cannot use sodium borohydride here, which we already talked about. Now in today's class, there is alcohol, that's how we made alcohol. Let's say we have alcohol, but we want to go back. How do we go back? We want to make carbonyl out of alcohol. How do I do that? We made alcohol out of ethanol reaction, right? We had another novel, not the first step, water, and as a result, we made alcohol, right? That's fine. But now let's say I have alcohol, I want to go back to carbonates. Here I have carbonates, I want to make alcohol. This is called reduction process. So you're taking down the oxidation level of carbon by adding hydrogen. Let's say bonded one, whereas this is bonded to oxygen, so to one bond. You have to also apply hydrogen. So if I were to go backwards, let's have to take carbon. How do I do this transformation? What do I do? We'll spend some time on that. So if I have to just oxidize an alcohol to an aldehyde state, I use simple reagents called PCC or PDC. These are like chromate salts. Chromium dioxide is an oxidant. But if you use chromium dioxide itself, it goes all the way to the acid. I don't want to go all the way to the acid, but if I need to go all the way to the acid, I can use chromium dioxide plus a little bit of acid. That's called Jones oxidation. Or I can also use that of it, like sodium dichromate. What is the formula for sodium dichromate? CaCl2O7, potassium dichromate, and a salt. What you have to notice that we are using metals with higher oxidation state. These are metal oxides, and they are oxidant, right? I can use KMnO4. I can use osmium tetroxide, but you don't use osmium tetroxide because it's positive reagent. But any of these, like manganese dioxide, can be used. But depending upon the oxidation level, if I use potassium permanganate here, I cannot stop at aldehyde state. I will go all the way to acid. So this is not going to cut my jaw if I have to take it to on that. So what we do is we tune these reagents a little bit and reduce the oxidation power. For example, manganese and would only go to RDI. So long. So we just want to do the simple transformation and then go to get solid RDI. Let's say I don't have manganese salt in the lab, I only have that chromium dioxide. So what I do is I take chromium dioxide and reduce it completely. Okay. If I just take pyridine and chromium dioxide, I make something called pyridinium dichlorophosphate. That's something here I make that. Don't have to know the structure of pyridinium dichlorophosphate. This side comes back, so we would get back to that structure. Okay. So depending upon the oxidation level that you want to achieve, whether you use milder oxidation reagent or you use stronger oxidation. Simple, right? So if I have to make an ester out of alcohol, what do I do? I first oxidize to carboxylic acid and then go to the ester. If I just want to oxidize an alcohol aldehyde, I will use milder reagent and then go to pyridinium chlorobromoate because in this combination and the result we can oxidize alcohol just to aldehyde state. If I want to go all the way to the acid, what happens is this goes first to the aldehyde state and the aldehyde immediately gets converted into acid. That cannot stop the second step, so I go all the way to the carboxylic acid. So depending upon what you have, what you want to do, you can pick the reagent. Let's say I have to do these two steps. Let's go to the aldehyde first, do the reagent, then I can add those reagents to this, those reagents to the oxidation of aldehyde to carboxylic acid. Those reagents is a mixture of chromium dioxide and sulfuric acid. Have you done this reaction in the lab? 2066 or 2065? Right? You took some alcohols and oxidized to respective products. If you have a secondary alcohol, what do I get? Let's say when I have secondary alcohol, that's the case with primary alcohol. Let's say I have secondary alcohol and I need to convert it. I can make any one of these reactions because this is the last stage. There's no further oxidation in our people. Because they cannot attach any more oxidation. So either I can use PCC or PDC or even flow. Even code or sorts of reagents can be used because there is no danger of more oxidation. That's the only oxidation that I can get. But when you have a primary alcohol, either you can go to aldehyde or you can go to carboxylic acid. So depending upon the state that you want to stop, you use reagents accordingly. If you use milder reagents, you stop at aldehyde stage. So you can potentially make aldehyde. If you want to make acid, then you use a stronger reagent. Give me 1 minute again, we'll reboot this and see how we can get this back. So in the afternoon recitation section today we'll practice the practice exam and see if you have any questions. But I cannot solve the whole practice exam. What I want to focus is on whatever the doubts you have. I'll be able to help you with that. So I suggest that you should go through the practice exam and come prepared so that we can have some meaningful discussions. Okay. So let's look into this oxidation quickly. Give me 5 minutes. So when you have primary alcohol, you can oxidize them by one level, that is aldehyde. If you further oxidize them, you get to carboxylic acid. Okay? So when you have primary alcohols, you got to be careful as to choose what reagent you want to choose. you have secondary alcohol, you can go only one stage, that's a ketone stage, so you don't have to be terribly worried about that reagent selection. But I'm not overly concerned about oxidation of this reagent, this reaction, because I can get only one product. If it's strong resistance or minor oxidant, I can only make ketone. But when I have a primary alcohol, I got to be careful as to select, so as to select the suitable reagent to stop at aldehyde stage or to go on the way to alcoholic acid. What happens when I have tertiary alcohol? Can I oxidize tertiary alcohol? No, I cannot oxidize tertiary alcohol. So some of these tertiary alcohols can be used as solvents because they cannot undergo oxidation reaction. Because that's all the carbon can make. It cannot make one more double bond to the oxygen. That would make carbon valence be 5, and that 5 is not allowed, and there is no leaving group on this one. If you have a leaving group, then probably that can take off, but the carbon-carbon bonds are difficult to break, so that doesn't happen. So the primary alcohol can be stopped at aldehyde by using a milder reagent, such as PDC and PCC, but if you have stronger reagents such as potassium permanganate, it goes all the way to carbonic acid. I cannot stop at in between stage. Okay? So this is one of the examples where you have an alcohol and you don't care about the product because it's called ketone, so I can use a stronger oxidant in this case. So secondary alcohols are no problem in oxidation. When you have primary alcohols, you got to choose them selectively. So this is a mechanism where chromium trioxide is used. So again, the same reaction, oxygen is acting as a nucleophile, it's attacking chromium, and the chromium complex gets formed, and again you have some basic species in the reaction medium, and as a result, finally the base comes and pushes proton, the electrons are pushed here, and the chromium salt gets broken, and the chromium goes from 6 to 4 or 5 lower oxidation state. This is undergoing reduction, as a result, this is undergoing oxidation. These are redox reactions, right? If something is undergoing oxidation, something has to reduce. This is undergoing reduction. You use chromium dioxide to make ketones and acids. But if I use chromium dioxide and a primary alcohol, I cannot stop at aldehyde state. It goes all the way to the carboxylic acid. So if I have to stop at aldehyde state, I have to use this pyridinium chlorochromate reagent. Pyridinium, because pyridine is in power form, and chromate is now tuned down. This is still the chromium salt, saying that the power of oxidation is being lowered a little bit compared to raw chromium dioxide. You are adding some pyridine so that you tone it down, and as a result, you can stop at aldehyde stage. Right? So if I use PCC or PDC, I can stop this oxidation of aldehyde. If I use this chromium dioxide, I will go all the way to carboxylic acid. Okay? So now we know how to go backwards and we know how to go forward. If I have a ketone, I can make this alcohol by using reducing reagent. If I have an alcohol, I can make carbon oxygen double bond. I get a carbon the aldehyde, ketones, and carboxylic acid by using oxygen reagent, which is called oxidation of alcohols. Right? So in the PowerPoint, I have summarized everything. What is the reagent? When is it used? What is the product? How is it done? Things like that. So take some time and go through these slides. There are various reagents, and then practice this problem. You should be outside for the exam. Okay? If you have any questions, after we'll talk about that.
Electrons, only difference between oxygen and sulfur is that oxygen only has up to